Welcome to this next lecture on acoustics. In the last class we had derived the green function, and we left it at a point where we said we will find an integral form of the wave equation, and the reason we will find an integral form is this. We have this PDE, let us say, now this PDE can be driven, okay, or excited, or input is given using initial conditions, which means pressure is given all over x at t equal to 0, and pressure is given, when we put a tilde, all over x, pressure dot is given at t equal to 0. These are the initial conditions. It can be driven by that. It can also be driven by boundary conditions. Okay. So, I have, let us say, a pipe, and at one end of the pipe, let us say, is a finite pipe and it is rigid ended. That means del P del x is 0, and here at x equal to 0 I have a piston, and the piston oscillates. So, this is a non-homogeneous boundary condition, non-homogeneous boundary condition. So, we can drive the system using initial conditions, we can drive the system using boundary conditions, we can also drive the system using sources. Okay. There is no source in here, we can put a source, okay, and that is what we did when we found the green function, is we put a point source. We put a point source and we found the response. We found the response, and that response is the green function. Now, what is the use of finding this green function? After having found the green function, if I have any other source, any other type of source, okay, then the response due to the source, due to the new source, is actually an integral of the green function with that source. Okay. That is the reason we find the green function. Okay. Now, so far we have spoken only about small g, which is, let us say, r comma r0, and which has the form e to the power of minus j k r minus r0 by 4 pi r minus r0. This is the free space green function. Now, the same equation can have other green function solutions. Can have other green function solutions. Now, how is that possible? We discussed it last time. So, now suppose I have a new green function which happens to be the free space green function plus some other function, and this some other function is such that del square plus k square gh equal to 0, then what happens? Then what I have is del square plus k square of this g is equal to del square plus k square of small g plus gh. Now, this operating on this gives me a minus delta function, and this operating on this from here gives me a 0. So, there is this now a new function g which satisfies this delta on the right side. So, this becomes g becomes a new green function, a new green function. Okay. And so, now for a given situation, let us say there is a source, there are some sources here, there is some rigid boundary, rigid sphere here, there is some rigid cylinder here in actual space. Okay. Now, for this configuration, maybe there is a wall here, for this configuration, if I can find a green function, can find a green function, that means I put a source somewhere here as minus delta r minus r0 and find the response in the presence of this cylindrical body and this spherical body and this wall, then that is my new green function g. Now, this g, in addition to satisfying the inhomogeneous Helmholtz equation, it satisfies conditions on these surfaces. On the surfaces. So, on this surface whatever be the boundary condition, this g satisfies that in addition to this inhomogeneous equation. Okay. So, now what happens is, now if we have actual sources, then the response is just an integral of this g I found and the distribution of sources. Okay. So, where was this? Yeah, this would be dV, let us say, over a volume. That would be the response, pressure response. Okay. So, that is why we try to find the green function, Okay. So far we have found only the free space green function. Okay. A little bit later we will find what is called the Dirichlet Green Function, okay, and so we will call it G with a D, and what this does is it goes to 0, GD is 0 on a certain surface, okay. Then we will find what we call the Neumann Green function. Find the Neumann Green function. What this does is, this is its normal derivative is 0 on a surface. Okay. So, there are many green functions. So, there is an advantage we will see a little bit later, and we are moving towards that. Okay. So, now what we are going to do is, in order to take advantage of the green function method, we will find an integral form for the wave equation. Okay, and it is called the Kirchhoff-Helmholtz integral equation. Or in short, it is called KHIE, and it is used very heavily in the boundary element method. So, numerical method, boundary element method. Okay. So, now let us start deriving the KH integral. KH integral. It begins with the Green's second identity, okay, Green's second identity. And what does it say? It says, if we have two functions that are finite, that means bounded, and have first and second let me put it the other way, have continuous first and second partial derivatives. Okay. In a volume V, and enclosed, that is, the volume is enclosed by a surface S. So, within this volume enclosed by a surface S, these two functions have first and second continuous partial derivatives, and let these two functions be denoted by phi and psi. Okay. Then the Green's second identity, okay. So, then then the volume integral of this phi, one of the functions, del square psi minus a psi del square of a phi over the volume is equal to the surface integral. So, let us call it the volume, let us call it the surface integral of phi del psi by del n minus psi del phi by del n over the surface. Okay. For now we will do the interior problem. Okay. For now we will do the interior problem. That means there is this volume that is bounded by a surface S, okay, and we are interested in the interior space. So, these two functions are well behaved inside, okay. These two functions phi and psi are well behaved inside this volume, okay. So, now how do we connect this to acoustics? We make a connection to acoustics now. And this is how we make the connection. So, let us say I have this volume here, okay, this is my volume bounded by surface S, okay. Then there is one set of sources, let us call it type 1, okay, they are acoustic sources. So, they are making sound, the sound waves they reach this volume, okay. And then there is another set of sources, okay, type 2, and let us say they are at same frequency, okay. So, now the Helmholtz equation, okay, Helmholtz equation, that means the time eliminated acoustic wave equation, for this set of sources, let us say the solution is phi, and for this set of solutions, let us say the solution is psi. So, now we have phi and psi inside this volume, okay. Now, this surface and volume are hypothetical, okay, they are not hard surfaces or anything, it is a hypothetical volume and hypothetical surface, just a mathematical construct, okay. So, now this will satisfy, the phi will satisfy the Helmholtz equation, so will psi, okay. So, what do we have here? We have del square plus k square of phi, I want to keep the line vertical, phi is equal to 0, okay, which means del square of phi is equal to minus k square of phi, and similarly del square plus k square of psi is equal to 0, implying del square psi is equal to minus k square psi within the volume, that is important, within the volume, not in the region where there are sources, not in this region. The region where the sources are will be singularities, okay. So, not in that region, but in the region where there are no sources, there are no sources here. In this region where there are no sources, phi and psi will be well behaved, and that well behavedness is shown by this satisfaction of the homogeneous wave equation. Okay, there is no inhomogeneity on the right hand side. Okay, and so we come up with this relationship. Now, if we use, so now phi and psi satisfy because we have second derivative, spatial derivatives. Okay, so the phi and psi satisfy the Green's second identity condition. Okay, so what do we have here now? We will have integral over the volume. I will just leave a one integral phi del square psi, if you remember, is minus k square psi minus a psi. Notice del square phi is minus k square of a phi over the volume dV is equal to the surface integral of phi del of psi dot n, okay, where this n points away from the region of interest. Okay. So, if we are interested in the interior space, n points outward. So, to complete this, this is psi into del phi dot n ds. Okay. Now, you can see that the left hand side is 0, left hand side is 0. So, what we have come up now is, if we have this volume inside which a certain phi and a certain psi are well behaved and they are solutions to the wave equation where the sources are outside, then integral over the volume, over the surface phi del psi dot n minus psi del phi dot n over this surface is equal to 0. Okay. So, this is what we have arrived at using the Green's second entity applied to this acoustic situation. Okay. Now let us see. I have this situation over here. This is my volume V, this is my surface S. So far the type 1 sources were here and they were making sound, and that solution was phi, and so I have phi in here coming from type 1 sources, and then I had this type 2 sources which were generating another set of sound field, and that was psi over here. Okay. Now what I am going to do, I am going to make psi the Green function, the free space Green function. Okay. Free space Green function. Okay, I am going to make psi the free space Green function. That means what? It satisfies del square plus k square psi is equal to minus, let us say, delta r minus r dash. Okay. in spherical coordinates. Let us take it as spherical, or let us keep it general for now. Okay. So now I have a point source over here, and that is generating a sound field. We will call that psi. Since the point source is outside my volume, phi and psi both are well behaved. You should remember that the Green function is unbounded at r equal to r dash. Okay. So it is not well behaved at r equal to r dash. So right now psi is well behaved. Why? Because the location r dash is outside. R dash, the location is outside the volume, so it is well behaved. Okay. Next what we will do is we bring in psi, we bring the source, the point source, we bring the point source into the volume V. Okay. That means we have this now we have a point source delta r minus r dash. This is my surface S, this is my volume V. Still the type 1 sources are doing their bit, they are sending in the solution phi. So phi is still there in here and well behaved, phi is still well behaved. That means second partial derivatives are continuous. But now psi is no more well behaved. Why? Because the source has come in, and psi is not valid at the location source location. Okay. Psi blows up, it is not bounded. Okay. So psi violates the, it is not finite, we said, right, we said finite here. So psi is now not finite within the volume. Okay. So we have this situation. So what now we are going to do is this here. We have to get back to our Green's identity. We have no other recourse. We have to get back to our Green's identity. Right now Green's identity is being violated by psi. Okay. So what now we will do is we will construct this volume V and this outer surface S, and we have a singularity here. We will enclose that singularity with a surface with epsilon radius, So this is a 3D volume, okay, volume 3D, and this is a sphere of radius epsilon that is enclosing this point r dash. Okay, this point is r dash measured from some axis, okay, and I am enclosing that point r dash by a sphere, very small sphere of radius epsilon. Okay. Now as a result, by excluding the sphere, by excluding the small sphere, okay, a new volume is generated. You have to give it a new name. A new volume is created or generated. Let's call it V dash, and a new surface comes up. Let us call it S dash, which is the original surface plus the surface of the epsilon sphere. Okay. Now within this new volume, V dash with surface S dash. Again Green's identity is valid. Why? Because in this new volume, the phi and psi, they do not have sources, they are away from sources, so they will satisfy the homogeneous Helmholtz equation. Okay. So then what? Then we can again apply on S dash. Now we can apply phi del psi dot n minus psi del phi dot n ds equal to 0, or ds dash, okay, sorry, S dash is the new surface. But what is this new surface? This new surface is old surface phi del psi dot n minus psi del phi dot n ds, original surface, plus another surface has come in, which is plus integral S epsilon, again phi del psi dot n minus psi del phi dot n ds epsilon, that is equal to 0. Okay. So we will call this 1, we will call this 2, okay, and we will look at 2, and within that there are 2 terms. So this is term 1, I will call this term A, we will call this term A, and we will call this term B. So let us look at term B, let us look at term B in 2. Okay. So here we will look at this term. Okay. So now what is that? So if we will write the entire 2, write the entire 2, it looks like this, it looks like integral S epsilon gradient phi gradient, okay, of the green function. What is the green function? It is e to the power of minus j k r minus r dash divided by 4 pi r minus r dash, okay, and this is on the epsilon sphere. We'll make it big. This is on the epsilon sphere of epsilon radius, and this is r dash, okay, and this point is r dash from some axis, this point is r dash, and r moves on the sphere, okay. So now this distance between the two r and r dash, the magnitude is epsilon. So this looks like e to the power of minus j k epsilon by 4 pi epsilon, okay. So if we put it in here, 1 by 4 pi e to the power of minus j k epsilon over epsilon minus 1 by 4 pi epsilon e to the power of minus j k epsilon and del phi dot n. Okay. So let's put an n over here. Okay, we still don't know what's going to happen, dotted with n. Okay. Now we said n points, n is the normal, and it points away from the area of interest, away from the volume, away from the volume of interest. Okay. So in here it points inward. I am interested in this area, so it points inward. So here it points inward. Okay. Whereas epsilon points, the scalar, it points from r dash towards r. Okay, it points from r dash towards r, that is epsilon. Okay. So what that means is that del n, del by del n is equal to minus del by del epsilon. Okay. So now we have the gradient, of this Green function expression dotted with n. So it is a directional derivative. So it is actually del by del n of this entity 4 pi e to the power of minus j k epsilon by epsilon, but now del n is minus del epsilon. So this becomes minus del by del epsilon of this term. So let us see ds epsilon. Okay. Now there is a lot of derivation that is left beyond this point. So I will close the lecture here for today, and we will continue in this in the next class. Thank you.